Hi everyone, my name is Sophie and I'll be going over section 15.1, which includes double integration using Riemann's integrals and Fubini's theorem. So first we're going to look at the double Riemann integral. So we have this here, where over a region of R, a function of two variables of x and y, where R is the rectangle, which is the Cartesian product of AB cross CD. So in the first example, I wanted to point out the 0, 2 cross 0, 1. This will always be x, and this will always be y. I also wanted to take a look at this. M equals n equals 2, which means that we will be dividing our rectangle by two rectangles across and two rectangles tall. So the first thing we are going to do is draw a picture of the rectangle with the volume sitting on that the rectangle is sitting on top of. We have been told that the interval for x extends from 0 to 2. So I'm going to make that 0, 1, 2. And our interval for y goes from 0 to 1. So 0, 1. We have also been told that m equals n equals 2. So we'll be dividing our rectangles by 2 across and 2 tall. So let's go ahead and draw our rectangle. And we'll be dividing by 2 across and 2 tall. So using the upper right corners, which I wanted us to use, we will plot our coordinates. So we're going to plot the upper right-hand corners of all our rectangles. So here we have 1, 1/2, 1, 1, 2, 1/2, and 2, 1. So that is everything we need to do to draw our two-dimensional xy coordinate plane. So the next thing we're going to do is, using this formula here, we're going to get an estimation of the volume, which tells us the exact volume that can be approximated by the Riemann sum if we take the limit of m and n as they go to infinity. So we will simplify ours because our m is 2, our I will be 1, and our n is also 2, and j equals 1. So this is what our simplified formula will look like. Delta A. So to get delta A, which is just the change in area for each rectangle, we'll go back to our drawing here, and we have 1 here and 1/2 here. So all we need to do is 1 times 1/2, which just equals 1/2. So back to our formula. We're going to plug in our coordinates that we got. So our volume will equal 1/2 1e raised to the negative 1/2 plus 1e raised to the negative 1 plus 2e raised to the negative 1 plus 2e raised to the negative 2. Okay, and this further simplifies, so we'll make that 3e raised to the negative 1, and we'll rewrite it as 1 over e raised to the 1/2 plus 2 over e plus 2 over e squared. And then finding the lowest common denominator, we get e3 plus square root of e plus 2 all over 2e squared. And plugging that into the calculator, we get 0.990. So that is how to solve an equation using Raymond's sum. So moving on to Fabini's theorem, we have this example here, which is square root of x over y squared dA over the rectangular region where x is between 0 and 4 and y is between 1 and 2. So Fabini's theorem tells us that if f is continuous, you can change the order you do the integration. So for this example, we're going to do it with respect to x. So if we're doing it with respect to x, and that is our equation there, we will write it out like this. So 0 to 4 and 1 to 2. X, and I'm just changing the square root here and rewriting it. Dx dy. And then that will equal, so we will be treating the y, because we're doing it with respect to x, we'll be treating the y like a constant first. So then that will become, this is 1 to 2, 2 over 3x raised to the 3/2 y negative 2. And that'll be from 0 to 4. And then plugging those in, we then get, that stays from, that stays from 1 to 2. And we get 16 over 3y raised to the negative 2 dy. Oh, I did want to point out, you should still carry the dy there. Don't forget that. And then further solving that, we will get negative 16 over 3y raised to the negative 1 from 1 to 2. And I'm just going to move back up to here. And we'll have negative 16 over 3 times 1/2 minus 1. And that equals 8 over 3. So that would be our final answer using Fabini's theorem. And again, if you did this in respect to y instead of respect to x, you would still get 8 over 3. You typically choose whether you want to do respect to x or respect to y, depending on which way would be easier for you to solve. So that completes section 15.1. Thank you for watching.